The English physicist and mathematician Isaac Newton was born on 1642 and died in 1727. He was a Lucasian professor of mathematics at the University of Cambridge and author of the Philosophiae Naturalis Principiae Mathematica. Newton is known widely for his laws of motion, universal gravitation, and motion of objects and planets derived mathematically from Kepler's laws. His extensive contribution towards mathematics include that of the general binomial theorem, which describes the general expansion of a binomial to a power, the approximation of roots, which involves finding an approximate value for the square root of a number, and using that identity to semi-accurately measure the actual square root. Newton's identities are series of equations giving relations to two symmetric polynomials, classified cubic plane curves, and approximated partial sums of harmonic series utilizing logarithms. Perhaps Newton's most recognizable achievement, however, is the joint independent creation of calculus with Gottfried Wilhelm Leibniz. This had begun initially as an attempt to find the slope at any given point on a curve whose slope was constantly varying. By taking the average gradient of a curve at increasingly smaller intervals, the derivative function, which he called the method of fluctuations, was found, which gave the gradient at any given point x, with an average gradient at an infinitesimal interval. Newton determined the area under a curve, or the method of fluence in his own terminology, by first calculating the momentary rate of change and then extrapolating the total area. He began by reasoning about an indefinitely small triangle whose area is a function of x and y. He then concluded that the infinitesimal increase will create a new formula where x equals x plus h. He then recalculated the area with the aid of the binomial theorem, removed all quantities containing letter h, and reformed an algebraic expression for the area. Removing quantities containing the letter h was the most significant part of this proof, due to terms multiplied it will be nothing with respect to the rest. At this point, Newton had begun to realize the central property of inversion. Newton had created an expression for the area under a curve by considering momentary increases at certain points. In effect, the fundamental theorem of calculus was built into his calculations. Newton credits these calculations to a realization that during his work on gravitation and other physical models, mathematics needed a new language to work with complex physical systems and variables, one that neither algebra nor geometry satisfied. Soon, other mathematicians, particularly Weierstrass and Cauchy, provided better methods denoted as delta and epsilons, and explanations for these same computational methods. Calculus has since been implemented into any field involving the mathematical modeling of a variable in a system in fields such as biology, statistics, economics, and physics. His model of calculus has been utilized in many other mathematical breakthroughs since his time, including the Fourier transform and the Gibbs principle. It is also worth noting that much of modern mathematics is derived from modern trends in calculus, and all modern scientific principles are expressed in the form of calculus. The ideas presented in statistics and numerical analysis derived from Newton's calculus and differential geometry presents the link between algebra and geometry by providing analytical tools to understand algebraic functions and the relation towards their physical presentation. These breakthroughs were only made possible by the rigorous treatment Newton and his contemporaries gave to calculus in their time.